Something has just appeared between 3i Atlas and Earth, and its arrival was a complete surprise until only 2 days ago. On the 2nd of November, the Russian astronomer Gennady Borisov, the very same one who discovered the second interstellar object ever recorded, located something new. It was a comet, but it was not just any comet. This one is in a position that defies any straightforward explanation. Its official designation is Comet Borisov, but the more unorthodox astronomers in the scientific community call it something else. They call it a probe. As of today, having passed weeks since its discovery, it occupies a place in our solar system that has unleashed an intense wave of discussions in the most serious scientific circles. The object exhibits a defined, sharp, compact, and clearly visible core. But what is truly disturbing is another detail. Its behavior does not match what ordinary comets do when they are at this distance from the Sun. Most of us have seen images of comets during our lives. All of them have a distinctive feature that defines them. The tail, that beautiful trail of gas and dust that shines against the black of space, pointing in the direction opposite to the Sun as if it were a cosmic flag. Comets develop tails because the heat from our star sublimates the ice in their cores, creating a wind of particles that the pressure of solar radiation pushes into space. It is a process so fundamental to the identity of comets that it is almost impossible to imagine one without it. But Comet Borisov shows none of that. It presents itself as a solitary light source, a dense and bright core that rests silently in the darkness and is situated almost perfectly on the line that connects 3i Atlas with our planet. This object emerged directly between the most anomalous interstellar visitor in recorded history and Earth. It appeared without a tail, without a coma that anyone could discern clearly, showing only a core. A core that was detected only because Borisov, with his half-meter telescope built by himself in Crimea, was casually exploring that precise region of the sky. On the night between the 1st and the 2nd of November, the Minor Planet Center issued the formal circular days later. 10 different observatories quickly confirmed the cometary activity. 10 separate facilities around the globe saw exactly the same thing, but here is where the story becomes deeply unsettling. While most astronomers in the world were completely focused on monitoring 3i Atlas, something else slipped silently into the intermediate space. Something that had been traveling on a trajectory that no one had predicted. Something that when finally detected showed characteristics so out of the ordinary that it forced scientists to question whether they really understand what they are observing. The question that now keeps the astronomical community on edge is a single one. Could Comet Borisov be something completely different from what we are assuming? Before continuing, I would love for you to write in the comments from where you are watching this video. It is always very special to know how far our stories reach. And if you are enjoying the content, consider giving it a like and subscribing to the channel. That helps me know if I am on the right track and if you want to see more videos like this. The story of how we arrived at this moment begins much earlier than Borisov's discovery. It begins with an object that revolutionized our understanding of the universe simply by existing. In the year 2019, telescopes detected for the first time an interstellar visitor that came from beyond our solar system. They called it Oumuamua, a Hawaiian word that means messenger from afar that arrives first, and indeed it was the first of its kind. The first that humanity had ever confirmed came from deep interstellar space. Oumuamua triggered a passionate debate throughout the scientific community. Astronomers debated fiercely about its nature. Some argued that it was an ordinary comet, simply one that had been ejected from its origin star system long ago. Others suggested more unusual features, anomalies in its movement that did not fit the models. The debate was intense, but eventually a general consensus was reached. Oumuamua was strange, yes, but probably natural. It was a reminder that space was full of objects we had never imagined. But Oumuamua was just the beginning because in 2019, just 2 years after Oumuamua, telescopes detected a second interstellar visitor. This object was discovered by the same Gennady Borisov, who would later discover the comet that bears his name. This second visitor was catalogued as 2i Borisov. And what 2i Borisov did was different. It had a tail. It had the behavior of a classic comet. It seemed more familiar, more predictable, more in line with what astronomers expected to see in an interstellar object. For years, 2i Borisov was studied extensively. The data it produced helped scientists develop models about how interstellar visitors would behave when they arrived in our cosmic neighborhood. Astronomers built equations, created simulations, tried to predict what kind of objects might travel through interstellar space and end up in orbits close to the Sun. All these studies produced a body of knowledge that seemed quite comprehensive, and then, in July of 2025, telescopes detected 3i Atlas, an object that would be massive, more massive than its predecessors, an object that would travel faster, an object that would exhibit anomalies so profound that they would make the mysteries of Oumuamua and 2I Borisov combined seem small. Astronomers thought they were ready. They believed they had the models, the theories, and the experience to understand what they were seeing. They were wrong because 3I Atlas would not only challenge their expectations, it would bring with it something that no one had fully anticipated. It would bring Comet Borisov, a secondary object that would seem to emerge from nowhere, positioned in a way that suggested an intention that astronomers did not know how to explain. 2 visitors instead of 1, 2 mysteries instead of 1, and the second would seem even more disconcerting than the first. To truly understand what makes Comet Borisov so unsettling, we need to first understand what makes 3I Atlas anomalous, because we cannot fully appreciate the disturbing features of Borisov's discovery without knowing the context of what preceded it. The 2 objects are inextricably connected, not only in space but in the mechanics of what both are telling us about our universe. When 3I Atlas was first detected, astronomers noticed something immediately. Its trajectory was peculiar. It was not arriving in our solar system from a random angle as a naturally ejected object from another star system would. Its orbit aligned almost perfectly with the plane of the ecliptic, that imaginary disk where the planets orbit. The mathematical probability of a natural interstellar object arriving in that specific alignment is extraordinarily low. Calculations suggest that the probability is less than 0.2%. But that was just the beginning. As 3I Atlas approached the Sun, it began to exhibit an acceleration that gravity alone could not explain. NASA instruments measured this deviation with a precision of 3.7 standard deviations, which in scientific language means that the phenomenon is real, not an instrumental anomaly or a measurement error. Something was pushing 3I Atlas, something that was not simply the gravitational pull of our Sun or the planets. Astronomers calculated that this non-gravitational acceleration implied that the object had lost more than 13% of its mass during its approach to perihelion. 13%. For an object of tens of billions of tons, this represented a colossal mass loss. More than 5 billion tons of material expelled into space. An amount so massive that it should have created a cloud of debris visible from ground-based telescopes, a plume of gas and dust so bright that it would be practically impossible not to see. But here is the strangest part. That cloud of debris never appeared. Images after its closest approach to the Sun showed 3I Atlas as a compact, defined, almost orderly object. There was no chaos of a catastrophic mass loss. There was no dispersion that physics would expect. There was simply a core that continued its journey. The scientific community found itself in an uncomfortable dilemma. The acceleration was a measurable fact. The mass loss was a logical conclusion based on well-established physical principles. But the visual consequences of that mass loss were completely absent. Something did not fit, something in the model of what they were observing was fundamentally wrong. And it was at this moment of deep perplexity when astronomers were still trying to reconcile these contradictory data that Gennady Borisov pointed his telescope toward a specific region of the sky. What he found there was not simply another ordinary comet. Gennady Borisov is an astronomer who belongs to a special breed of scientists. He does not work in a large observatory funded by governments or universities. He built his own telescope with his own hands in Crimea. A half-meter aperture mirror crafted with the precision of someone who has dedicated years to perfecting his craft. Every clear night, Borisov goes out to observe the night sky, scrutinizing specific regions of the firmament that other astronomers are not actively monitoring. He is a manual observer in an era of automation, a comet hunter in the most traditional sense of the word. While the world's large observatories keep their eyes fixed on predetermined targets, Borisov moves with a freedom that allows him to explore. And it was this freedom, this willingness to simply look toward a region of the sky without a preset agenda, that led him to his most disturbing discovery. On the night of the 1st to the 2nd of November, Borisov pointed his telescope toward the region where 3I Atlas had been situated just 4 days earlier. 3I Atlas had completed its closest approach to the Sun. The object was emerging from solar conjunction, that period when the Sun's light makes it impossible for ground-based telescopes to observe objects that are too close to our star. It was the perfect moment to resume observations now that the object was visible again. But what Borisov saw was not simply 3I Atlas. He saw something else, something that stood between the main object and Earth, something that had been traveling in the space presumably for weeks, without having been detected by any of the automatic surveillance systems that constantly scan the night sky, none of the satellites, none of the automatic observatories, only Gennady Borisov looking by chance in the right direction at the exact moment. The Minor Planet Center was notified immediately. The data were verified. Other observatories were alerted to confirm the discovery, and in a matter of hours 10 separate facilities around the globe were pointing their instruments toward the coordinates that Borisov had provided. 10 different observatories using different equipment controlled by different astronomers, and all of them saw exactly the same thing. An object that exhibited a coma, that diffuse envelope of gas around a comet's core, but the coma was small, unusually small for the distance at which the object was from the Sun. And even more disconcerting, those 10 observatories reported only the faintest evidence of a tail. An incipient tail that barely extended from the core, measured at only 7 arcseconds. For an object that had been moving away from the Sun for several days, it should have developed a much more pronounced and bright structure. The object's brightness was measured at a magnitude of 12, faint enough to require specialized equipment to observe it, faint enough to go completely unnoticed if someone were not specifically looking in that exact direction, but bright enough to have been detected weeks earlier if someone had been monitoring that region of space. No one was. For weeks, worldwide astronomical attention had been completely concentrated on 3I Atlas. Every available observation window in Earth's most powerful telescopes had been assigned to monitoring this massive interstellar object. Every press release issued by the large observatories focused on it. Specialized scientific journals dedicated entire articles to its unique features. The general public was captivated by the stories of this mysterious visitor from deep space. And while the entire world kept its attention focused on a single point in the sky, something else was slipping silently through space. Completely unnoticed. Comet Borisov had been traveling through the inner solar system for weeks without anyone knowing, without any automatic detection algorithm capturing it, without any observatory recording it. It was traveling on a trajectory that would take it directly between 3I Atlas and Earth, as if it were deliberately positioning itself in that intermediate space. This is not a minor detail. It is deeply significant when we consider what it means for the statistical probability of 2 interstellar objects arriving in our solar system, not only simultaneously, but in such a specific geometric configuration. Orbital mechanics suggest that interstellar objects should arrive from practically random directions. They should pass through our solar system on trajectories that reflect the fundamental randomness of the universe. But Comet Borisov did not arrive randomly. Its discovery was just 4 days after 3I Atlas completed its perihelion, its closest approach to the Sun. Astronomers studying the data began to ask questions. How long had Comet Borisov been traveling in this region of space? When exactly did it enter the solar system? Was it following an independent trajectory or was it somehow connected to the main object? Orbital analyses began immediately. Astronomers used observations from multiple telescopes to triangulate the object's exact position. They calculated its speed by measuring how its position changed night after night. They determined its trajectory by projecting it backward in time to see where it had come from. And when they completed these calculations, they discovered something that intensified the mystery even further. Comet Borisov was following a hyperbolic trajectory. This means that it was doomed to leave the solar system forever. It was not captured by the Sun's gravity. It would not return, but more importantly, its trajectory would take it to pass at only 0.69 astronomical units from Earth. To put this in perspective, 1 astronomical unit is the distance between Earth and the Sun. 0.69 astronomical units equals approximately 103 million kilometers. In cosmic terms, this is extraordinarily close. Not close enough to cause alarm about an impact. Not close enough to represent an immediate danger. But close enough that if this object had observation equipment, if it had instruments capable of collecting data about our planet, this would be the ideal geometry to do so. The scientific community found itself facing an increasingly complex landscape. They had a massive interstellar object that exhibited profound anomalies. They had a second object that appeared in a geometrically significant position, and they had a temporal coincidence that simply could not be easily ignored. 4 days? That was the interval between the perihelion of 3I Atlas and the discovery of Comet Borisov. Astronomers began to pose questions that years earlier would have been considered marginal or outside the scope of serious science. Was there a causal connection between these two events? Was it possible that Comet Borisov was somehow related to 3I Atlas? Could the smaller object be material expelled from the main object during perihelion? To answer these questions, scientists needed to understand exactly how much mass 3I Atlas had lost. It was not enough to simply measure the non-gravitational acceleration. They needed to calculate the specific amount of material that had been expelled. The calculations were based on fundamental physical principles, specifically the law of conservation of linear momentum. When an object loses mass, the material that leaves the main body must carry momentum with it. Therefore, the main body experiences a recoil in the opposite direction. By measuring this recoil, measuring the acceleration that could not be explained by gravity, astronomers could work backward mathematically to determine how much mass had been expelled and at what speed. The calculations performed by astrophysicists from recognized institutions suggested that 3I Atlas had lost more than 13% of its mass. Total, for an object estimated at tens of billions of tons, this represented an extraordinary loss. More than 5 billion tons. That is a number difficult to comprehend. It requires context to truly appreciate it. 5 billion tons is approximately the mass of a medium-sized mountain. It is the amount of material that could fill volumes measured in cubic kilometers. It is an amount so vast that it simply does not disappear without leaving an observable trace. Yet that is exactly what seemed to have happened. Observatories that scanned the region around 3I Atlas after its perihelion did not detect the massive cloud of debris that should accompany a mass loss of that magnitude. Images taken in the days after the event showed 3I Atlas as a compact defined object without the expansive halo of gas and dust that physics would demand. Some astronomers suggested that the cloud might have dispersed too quickly to be detected. Others argued that the material might have been directed preferentially in one direction rather than dispersing in all directions. But these explanations required invoking increasingly specific and less probable circumstances. Then a question arose that a few astronomers began to pose with greater seriousness. What if those 5 billion tons had not dispersed at all, and what if instead they had remained cohesive, traveling as a unit or a small group of objects along trajectories determined by something more than random natural forces? If those 5 billion tons did not disperse but remained cohesive, then the next question was inevitable. Where did they go? Where is the material that was expelled from 3I Atlas? It cannot simply disappear from the universe. The laws of physics do not allow it. Matter is conserved, it transforms, it redistributes, it changes state, but it does not disappear. Astronomers examined the available data with renewed intensity. The spectroscopic, the photometric, the multi-wavelength images. They looked for any hint of dust, ionized gas, expanding material, anything that could reveal where the lost mass had gone. And it was precisely during this search that patterns began to emerge. The material expelled from 3I Atlas during perihelion would have experienced specific forces at that moment. The Sun's gravity would be maximum at perihelion, the orbital speed would also be maximum. A principle of orbital mechanics known as the Oberth effect dictates that propulsion maneuvers are most efficient at the point of highest speed in an orbit. For an object passing through the inner solar system, that point is precisely perihelion. Aerospace engineers understand this perfectly. They know that if they want to send a spacecraft to a specific destination, perihelion is the ideal moment to execute the maneuver. Speed is maximum. Available energy is maximum. The change in velocity that can be achieved with a given amount of fuel is maximum. It is an opportunity window that space mission planners actively seek. And if 3I Atlas were using precisely this principle, and if what appeared to be a non-gravitational acceleration caused by natural outgassing were actually a deliberate velocity change, and if the expelled mass were not accidentally lost material, but material deliberately directed towards specific trajectories, Comet Borisov, positioned directly between 3I Atlas and Earth, began to seem less like a cosmic coincidence and more like evidence of deliberate intention, not like a random fragment expelled during a chaotic cometary eruption, but like something that had been sent to a specific position following a carefully calculated trajectory. Astronomers who began to explore these connections faced an uncomfortable tension. Explanations based on random natural processes required invoking increasingly improbable coincidences. Explanations based on the possibility of intelligent design offered a framework that explained all the observed data in a cohesive and elegant way. But admitting this meant crossing a threshold. It meant seriously considering the possibility that what they were observing might not be a natural phenomenon, but a technological artifact. It meant contemplating the idea that another civilization originating from another star system might have sent an explorer through interstellar space to investigate our corner of the universe. It was a radical claim, and yet the data seemed to point directly to it. Before they could fully understand what Comet Borisov might mean, astronomers needed to step back and examine more carefully the behavior of 3I Atlas during its approach to the Sun. The data they collected during this critical period revealed details that had been overlooked in the initial analyses. The object was not simply experiencing constant acceleration. Its behavior was more complex, more deliberate, more indicative of something that was being actively controlled. In the weeks leading up to perihelion, astronomers observed that 3I Atlas began to deviate its trajectory in ways that could not be explained solely by gravity. These deviations were small at first, measured in tens of kilometers across millions of kilometers of distance. Small perturbations that could easily have been attributed to measurement errors or uncertainties in orbital calculations. But as the object approached closer to the Sun, as it neared perihelion, these deviations grew. By October, when 3I Atlas was only weeks from its closest approach to our star, the difference between where the gravitational models predicted the object would be and where it actually was had grown to levels that could not be ignored. It was measurable, it was consistent, it was real. NASA officially attributed these deviations to outgassing. It was the standard explanation that astronomers offered whenever a comet deviated from its predicted path. Gas escaping from a comet's surface acts like small thrusters, pushing the object in directions that gravity alone would not predict. It was a perfectly reasonable explanation, except for one fundamental problem. The outgassing explanation required that there be evidence of that outgassing, it required seeing the gas being expelled, it required detecting the spectral lines of ionized gas. It required observing variations in brightness as dust reflected sunlight. In short, it required a massive debris cloud, exactly like the one that simply did not appear in the post-perihelion observations. If 3I Atlas had expelled enough gas to measurably alter its trajectory, that gas would have to be somewhere. It could not simply disappear. But when observatories searched for this evidence, when they scanned the region around the object in multiple wavelengths, they did not find what they expected to find. Images taken by professional ground-based observatories showed 3I Atlas as a compact light source. Spectroscopic data were consistent with a comet, yes, but a comet that exhibited activity less than what the measured acceleration should have implied. Hubble Space Telescope images confirmed that the object had a diffuse coma around its core, but this coma was surprisingly small for an object that supposedly had lost 13% of its mass. It was as if the object had experienced a catastrophic mass loss, but without exhibiting any of the visual signs that this catastrophe should have left. It was as if the mass had been expelled in a controlled, directed, intentional manner, rather than simply being torn from the object by the sun's heat, as would occur in a random natural process. What astronomers needed at this point was a deeper understanding of what exactly constituted the activity of 3I Atlas during its critical approach to the Sun. Spectroscopic data provided clues, but these clues were often ambiguous, subject to multiple interpretations. Analysis of the light reflected and emitted by the object showed chemical signatures, but determining exactly what these signatures meant required making assumptions about processes that could not be observed directly. What was undeniable, however, was that 3I Atlas exhibited anomalous coloration during its approach to perihelion. Photometric data collected by multiple independent instruments showed that the object had acquired a notably blue hue. This was not an artistic representation or a false color composite designed to enhance specific features. It was the actual analysis of the wavelengths of light that the object was reflecting or emitting. Color in astronomy is not decorative, it is not subjective. Color tells us about real physical processes. Blue color implies higher energy photons, shorter wavelengths. Blue color suggests higher temperatures or specific energy sources. Blue color in a comet is something unusual. Comets tend to show reddish or orange tones because the dust surrounding their cores scatters the longer wavelengths of sunlight. When Gennady Borisov observed the blue hue of 3I Atlas during its perihelion approach, he began to ask questions about what this might mean. Astronomers reviewing spectral data in scientific journals found themselves debating possibilities. One natural explanation suggested that ionized carbon monoxide emitted blue light. Carbon monoxide is a common cometary gas. When intense ultraviolet radiation from the sun strips electrons from carbon monoxide molecules, the resulting ions glow blue as the electrons recombine. This was an explanation that fit within well-established natural frameworks. It invoked nothing exotic, but it required that 3I Atlas had expelled enormous amounts of carbon monoxide, amounts so massive that they dominated the complete coma spectral signature. And again, any expulsion of gas of that magnitude should leave an observable trace in the form of a visible debris cloud. Yet other astronomers noted that blue color could also be explained by less natural processes. Rocket engines burn blue when the combustion temperature is high enough. Nuclear reactors produce Cherenkov radiation, that characteristic blue glow seen in the water surrounding reactor cores. Ion propulsion systems emit blue light as charged particles are accelerated through electromagnetic fields. It was speculation certainly, but it was speculation based on valid physics, on known processes, on technology that humans had already developed and fully understood. Astronomers who raised these ideas were not suggesting that 3I Atlas was definitely propelled by extraterrestrial technology. They were only pointing out that the observational data did not exclude this possibility. The color change persisted. Subsequent observations confirmed that the blue was not a passing effect. It was a consistent feature of the object during its perihelic phase. While astronomers debated the meaning of the blue color of 3I Atlas, another aspect of the object's behavior demanded equally urgent attention. NASA's Europa Clipper probe, a flagship mission en route to Jupiter's moon Europa, was traveling through the inner solar system space. Exactly at the moment when 3I Atlas completed its approach to the Sun, the orbital geometry suggested that the Europa Clipper would pass dangerously close to the ionic tail that 3I Atlas was producing as it approached our star. Ionic tails are structures distinct from the more familiar dust tails we see in classic comet images. While dust tails form when solar radiation pressure pushes dust particles away from the core, creating that characteristic curved structure, ionic tails are formed when the solar wind strips electrons from neutral gas atoms. The resulting ions follow the lines of the interplanetary magnetic field and extend in practically straight lines from the comet into space. The Europa Clipper carried on board a sophisticated suite of scientific instruments designed specifically to characterize the space environment. The onboard mass spectrometer could identify specific molecules with extraordinary precision. The dust analyzer could measure the composition and velocity of individual particles. The magnetometer could map the structure of magnetic fields with both spatial and temporal resolution. These were not instruments that remained idle during the mission's cruise phase. They were operational, continuously collecting data as the spacecraft traveled toward Jupiter. And between late October and early November, the Europa Clipper was positioned in such a way that its orbits potentially intersected with the ionic tail of 3I Atlas. The encounter, if it occurred, would have provided unprecedented data. Never before in the history of human space exploration had a spacecraft directly sampled material from an interstellar object. Never before had astronomers had the opportunity to analyze in situ particles and gases from a visitor from deep space. If the Europa Clipper passed through the ionic tail, its instruments would have collected information that would definitively answer many of the questions surrounding the nature of 3I Atlas. The mass spectrometer would have measured the isotopic ratios of the material, potentially revealing which star system it originally came from. The dust analyzer would have characterized the size, structure, and composition of the particles, determining whether they were consistent with normal cometary dust or whether they exhibited anomalous features. The magnetometer would have mapped how the material from 3I Atlas interacted with the interplanetary magnetic field. However, when the scientific community looked for the data from this potentially revolutionary encounter, it was met with silence. NASA did not publish the results, did not issue press releases about the measurements, did not share the data with the international astronomical community. The potential encounter of the Europa Clipper with the tail of 3I Atlas was simply not mentioned in the agency's official communications. It was an absence that spoke volumes, it was a silence that generated questions. The absence of data about the potential encounter of the Europa Clipper with 3I Atlas was not an isolated event. It was part of a broader pattern of information withholding that was beginning to characterize how space agencies handled data related to this interstellar object. While some observatories published images and analyses, others kept their data under lock, invoking administrative reasons or review protocols that extended indefinitely. NASA, in particular, found itself in an uncomfortable position. It possessed ultra-high-resolution images of 3I Atlas, captured by the Mars Reconnaissance Orbiter when the object passed at only 29 million kilometers from Mars in early October. These images had been taken by the High-Resolution Imaging Science Experiment camera, an instrument with a 50-centimeter aperture mirror, capable of achieving a resolution of 30 centimeters per pixel. To put this in perspective, that was 3 times better than the best images obtained by the Hubble Space Telescope on the 21st of July. Such extraordinary resolution would have allowed astronomers to distinguish structures on the object's surface. It would have revealed patterns of fragmentation or gas jets. It would have shown whether the object was a solid monolithic body or a loose aggregate of fragments barely held together. It would have provided definitive answers to questions that had been pursuing the scientific community for months. But these images were not published. Weeks passed, then months. The official justification was that the United States federal government had experienced an administrative shutdown. Funding had expired. Non-essential personnel were furloughed. Data processing channels were frozen. Review processes were halted, public communications ceased. In theory, this made sense. Governments occasionally experience pauses in their operations when legislatures fail to reach budget agreements. Agencies are forced to suspend non-essential activities. Personnel are forced to wait at home without pay. It is a frustrating administrative process, but not without precedent. However, when examined more closely, the shutdown explanation began to show cracks. Other components of NASA continued to function normally. The James Webb Space Telescope continued to publish images. Hubble proceeded with its observation schedule. Martian rovers continued to send photographs. The Europa Clipper probe transmitted its telemetry. Somehow, the administrative paralysis seemed to affect only the specific data that the entire scientific community longed to see. A congresswoman from Florida named Ana Paulina Luna recognized this incongruity. On the 31st of October, she sent a formal letter to the acting administrator of NASA. In the letter, she requested the immediate publication of the observational data related to 3I Atlas, including specifically the images from the high-resolution imaging science experiment camera, as well as additional information about interstellar objects of scientific interest. Luna was explicit about the urgency. She argued that this information possessed capital importance to advance the understanding of interstellar visitors and their interaction with the solar system. Her political pressure led to promises that the data would be published as soon as the government resumed its operations. But that resumption was delayed, and meanwhile, Comet Borisov continued its journey, slowly moving away from Earth. While the scientific community waited for NASA to publish its high-resolution images, other space agencies were taking different actions. The European Space Agency did not face the same administrative restrictions that paralyzed the American agencies. It operated independently of United States internal politics. Its missions, including Mars Express and the ExoMars Trace Gas Orbiter, had attempted to photograph 3I Atlas during its flyby of Mars in early October. The ExoMars Trace Gas Orbiter, equipped with cameras designed specifically to study the Martian atmosphere in ultra-high resolution, pointed those instruments toward 3I Atlas during the encounter. The orbiter captured hundreds of frames, hundreds of images that showed the interstellar object from multiple angles under different lighting conditions, using various image processing techniques. However, when the European Space Agency published its findings, something disconcerting happened. The European Space Agency, which was typically as transparent as any modern scientific institution, published exactly 2 images, 2 of the hundreds it had captured, 2 snapshots that showed 3I Atlas as a diffuse white point against the black of space. Nothing more, without any explanation of why only 2 images had been selected for publication, without comments on what the other 488 images that remained under lock and key showed. It was a disconcerting pattern. An agency that did not face the same administrative restrictions as NASA, an agency that operated under principles of international scientific transparency, was suddenly being selective in a way that contradicted its established practices. Astronomers found themselves with a puzzle. If the additional images showed exactly what the 2 published ones showed, why not simply publish them all? Why the restrictiveness? China, for its part, acted differently. The China National Space Administration released images captured by the Tianwen-1 Martian orbiter on the 3rd of October. The photographs showed the core of 3I Atlas enveloped in a coma whose diameter extended between 5,000 and 10,000 kilometers. They were images of valid scientific quality. They showed details that ground-based telescopes simply could not resolve. The high-resolution camera on board Tianwen-1 had a primary mirror of 38.7 centimeters in diameter, slightly smaller than that of the high-resolution imaging science experiment, but still capable of revealing details invisible to ground-based telescopes. The China National Space Administration acknowledged in its statement that photographing a target so distant and relatively faint, between 10,000 and 100,000 times darker than the features on Mars's surface, represented a considerable technical challenge. Despite this, they did it. They published the images, contributed to the worldwide scientific effort without demanding that international politics submit to bureaucratic convenience. What emerged from these different approaches was a disturbing contrast. The American agency with the best images remained silent. The European agency with similar capabilities was selective in its disclosure. The Chinese agency with slightly lesser capabilities published freely and openly. It was a pattern that raised deep questions about what might be motivating these different responses. To truly understand what these high-resolution images might have revealed, we need to consider what specific questions astronomers hoped could be answered through direct high-resolution observation. Spectral data provided information about chemical composition. Astrometric measurements provided information about trajectory. But there were structural details, geometric details that only an ultra-high-resolution image could resolve. Was 3I Atlas a single solid body or a loose aggregate of fragments barely held together by weak gravity? This was a fundamental question. Typical solar system comets that have been photographed up close by space probes frequently turn out to be aggregates of this type. Porous and low-density structures that seem more like piles of rubble weakly gravitationally bound than solid monolithic objects. But the distinction was important. A monolithic object suggests a body that has remained intact for billions of years of interstellar travel. An aggregate suggests an object that has fragmented at some point in its history. Did the object show signs of artificial geometry? Were there features on its surface that suggested it was not simply the product of random accretion processes? Natural structures tend to have irregular, asymmetrical shapes, the product of random collisions and fragmentations. Natural surfaces tend to be rough and chaotic, but a technologically constructed object might exhibit edges, flat surfaces, geometries that suggested intelligent design. Were jets of matter visible, localized sources of outgassing? If 3I Atlas was experiencing outgassing, it would not necessarily have to be uniform around the object. Outgassing could concentrate in certain regions, creating jets that would be clearly visible in ultra-high-resolution images. If the outgassing was intense and localized enough, it could explain both the measured acceleration and the absence of a dispersed debris cloud if the material were expelled preferentially in one direction. Was the object's surface uniformly inert and inactive, inconsistent with the mass loss that the non-gravitational acceleration required, or, on the contrary, did it show signatures of intense activity, bright regions, patterns that suggested energetic processes occurring on the surface? The high-resolution imaging science experiment images had the resolution to answer all these questions. They had the potential to distinguish between an unusual natural object and something that simply did not fit into the categories that science had developed to classify celestial bodies. They had the power to resolve the mystery in a way that no other dataset could. Yet these images remained unpublished. Astronomers continued working with incomplete information, trying to build models based on fragmentary data, trying to reach conclusions with only a fraction of the available evidence. It was a frustrating situation. It was a situation that generated speculation about the reasons behind the information withholding. Scientists who were publicly studying the available data began to ask uncomfortable questions. What could an image of such quality show that would justify such a level of information retention? While some astronomers focused on the images that were not being published, others directed their attention toward a different but equally disturbing aspect of the behavior of 3I Atlas. The object had exhibited changes in its brightness that defied simple explanation. It was not simply that the object became brighter as it approached the sun, which was completely expected. It was the specific nature of these brightness changes. Comets typically experience a gradual increase in their luminosity as they approach the sun. This increase follows predictable power laws based on distance and solar flux. Astronomers can calculate with reasonable precision how a comet's brightness should change knowing simply its distance from the star. It is one of the most predictable behaviors of these objects, but 3I Atlas did not behave predictably. Photometric data showed that the object had experienced brightness increases that were more abrupt and more dramatic than what the models predicted. In particular, the object had quintupled its brightness in the green light band during its approach to perihelion. A luminosity change of that magnitude was extraordinary. It was the type of change that would suggest that something had been activated, that some process had begun operating at a different level. Comets can experience abrupt brightness changes under certain circumstances. If fresh ice is suddenly exposed to solar radiation, for example, if the collapse of a crater reveals material that has never before been irradiated, the object can flare suddenly. But these events are ephemeral. The increased brightness disappears in hours or days as the new surface becomes covered with dust again. The brightness increase of 3I Atlas was different. It was persistent, it was sustained, it was consistent with a change in the fundamental level of activity of the object. As the object approached closer and closer to the sun, as it experienced increasing levels of solar radiation, its brightness remained at these elevated levels. It did not decrease, it did not dim, it remained. This persistence was significant. It suggested that something more than simple solar heating was occurring. Astronomers analyzing the data speculated about what could cause such behavior. There could be solar panels on board the object that were orienting optimally to collect solar energy. Solar energy is a well-known technology used in human spacecraft. There could be solar thermal collectors that were being deployed as the object approached perihelion. Perihelion is the point of maximum efficiency for any system that depends on solar energy. It is the moment when an object receives the maximum amount of solar radiation per unit area. If something on board 3I Atlas were designed to operate better under these conditions, perihelion would be exactly when we would expect to see it functioning at maximum efficiency. The sudden and persistent brightness increase was consistent with the activation of solar energy systems during perihelion. It was a feature that physics could easily explain if one allowed contemplating certain types of hypotheses that institutional astronomy generally avoided. While some explored these mysteries of the behavior of 3I Atlas, astronomers could not help constantly returning to the central question that had emerged from the very first moment. What was the nature of Comet Borisov? Why did this object appear precisely when it did? Why was it positioned exactly where it was? These questions intertwined with the mysteries of the main object, creating a fabric of anomalies that reinforced each other. Orbital analyses of Comet Borisov revealed details that only intensified the mystery. The object followed a hyperbolic trajectory, meaning it was not gravitationally bound to the Sun. It would not return. It was doomed to leave the solar system forever after its passage. Its orbital inclination reached approximately 112 degrees, indicating retrograde motion. It was traveling backward in relation to the direction in which the planets orbit around the Sun. Retrograde motion is not impossible for interstellar objects. It occurs, but when combined with all the other features of the object, when considered alongside its position, its discovery timeline, its absence of a tail, it began to form part of a pattern that was difficult to explain through pure coincidence. Comet Borisov would reach its closest approach to Earth on the 11th of November, exactly 9 days after 3I Atlas completed its perihelion, exactly 9 days after the massive mass loss of 3I Atlas had occurred. At its closest point it would pass at 0.69 astronomical units, which equaled approximately 103 million kilometers. In cosmic terms, that was extraordinarily close. Not close enough to cause damage, not close enough to threaten civilization, but close enough that if this object had observation instruments, if it had the capacity to collect data about our planet and our civilization, this would be the ideal geometry to do so. Astronomers who considered the hypothesis that Comet Borisov might not be a comet at all, that it might be something completely different, something that had been deliberately positioned in this region of space, had to consider a fundamental orbital mechanics principle. The Oberth effect, a principle named after the German physicist Hermann Oberth, states that propulsion maneuvers are most efficient at the point of highest speed in an orbit. Before continuing, I would love for you to leave in the comments what topics you would like to see here on the channel. It is always very special to be able to bring content that really interests you. And if you are enjoying the video, do not forget to give it a like and subscribe to the channel. That way I know I am on the right track and that you want to see more videos like this. For an object passing through the inner solar system, that point was perihelion. It was the moment when orbital speed was maximum. It was the moment when a deliberate velocity change produced the maximum change in kinetic energy per unit of propellant expended. It was the ideal moment to execute any maneuver that required a significant change in trajectory. If 3I Atlas were a mothership that wished to deploy smaller probes toward specific positions in the solar system, it would choose to do this during perihelion. It would choose that moment to release its payload, to impart the necessary velocity changes, to send its explorers in specific directions. 9 days of transit time was a plausible interval for an object to travel from the position of 3I Atlas at perihelion to the vicinity of Earth. The numbers fit, the geometry worked, the timeline was coherent. The astronomical community found itself at a profound inflection point. The data were there, the anomalies were real, the measurements were valid, but the interpretation of these data led to conclusions that challenged the established scientific consensus. It was a moment when astronomers had to choose between clinging to increasingly complicated explanations or seriously considering the possibility that they were observing something fundamentally different from what they had expected to find. Some researchers with impeccable credentials began to articulate these ideas publicly. They were not making definitive claims. They were not insisting that 3I Atlas was definitely a spacecraft. What they were saying was that the data did not exclude this possibility. They were pointing out that any honest scientific investigation required considering all hypotheses that could explain the observations, even those that challenged conventional thinking. An astrophysicist from Harvard who had dedicated years to the study of interstellar objects and who had systematically documented the anomalies of 3I Atlas began to publish detailed analyses about what the data were really saying. His writings were careful, precise, full of appropriate qualifications. He did not pronounce definitive judgments, but he allowed the data to speak for themselves. And the data, when examined holistically, painted a picture that was difficult to reconcile with purely natural explanations. This scientist calculated the compound probabilities. If each anomaly had a small probability of occurring by chance, the probability of all occurring simultaneously in a single object was the mathematical product of those individual probabilities. The resulting number was extraordinarily small, 1 part in 10,000 trillion, a number so minuscule that invoking chance required more faith than invoking design. His analysis was rigorous, his calculations were verifiable, his conclusions followed logically from his premises. And yet, when these analyses were shared with the wider scientific community, the response was mixed. Some scientists recognized the rigor of the work, others dismissed it automatically, arguing that no matter how rigorous the calculations were, the conclusion was simply too radical to be considered seriously. But there was a fundamental problem with this dismissive attitude. Science should not work that way. Science should allow the data to guide the conclusions, not allow prior preferences to determine which data are worthy of consideration. If the data pointed toward an uncomfortable conclusion, the task of scientists was to investigate that conclusion further, not simply dismiss it because it was uncomfortable. The astrophysicist in question had pointed out this logical inconsistency in several of his writings. He had argued that the scientific community was allowing itself to fall into a cognitive bias, a prejudice toward explanations that fit previously established models. He had suggested that this was especially problematic in a situation like this, where the data were genuinely novel, where the objects under study had no clear precedents in the astronomical records. The institutional response was considered defensive. Spokespeople from the large space agencies issued statements that characterized these speculations as pseudoscience. Critics within the academic community suggested that allowing such thinking damaged the credibility of professional astronomy. And yet, the data did not simply disappear because institutional scientists decided to ignore them. What made the analysis of these data particularly disturbing was that it was not being carried out by marginal researchers or by fringe scientists working from basements or garages. It was being carried out by scientists with impeccable credentials, with extensive research trajectories, with peer-reviewed publications in high-prestige journals. These were researchers who had dedicated their careers to rigorous astronomy and careful scientific thinking. The astrophysicist in question had chaired the astronomy department at Harvard for 9 years. He directed the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. He led the Galileo Project, a serious scientific effort dedicated to the search for evidence of extraterrestrial technology. He had published hundreds of peer-reviewed articles on topics ranging from black holes and cosmology to the first stars of the early universe. When someone with that trajectory, with that institutional position, with that level of credibility within the scientific community, suggested that perhaps we should consider the possibility that 3I Atlas was of technological origin, it was not wild speculation coming from the margins of science. It was a testable hypothesis being proposed by someone who fully understood what kind of evidence would be necessary to support or refute it. This scientist understood that unfounded speculation had no value in science, but he also understood that dismissing speculation based on problematic hypotheses had no value either. His position was that any honest investigation required taking seriously all hypotheses that could explain the observational data, that experiments be designed or observations carried out that could distinguish between alternatives, and that the evidence be allowed to guide the conclusions. What differentiated him from many of his critics was that he explicitly recognized the uncertainty. He did not insist that 3I Atlas was definitely of technological origin. He pointed out that the data did not exclude this possibility. He pointed out that it was incumbent on the scientific community to investigate this possibility seriously, rather than dismiss it reflexively. When presented with criticisms of his analyses, his response was consistent. He pointed out that science advances by considering possibilities that seem improbable until the evidence forces us to reconsider them. He pointed out that prior judgments about what is possible or probable should not determine what we investigate. He pointed out that the scientific method required that we follow the evidence wherever it leads, even if it leads to places we find uncomfortable. This perspective resonated with many people, not because they wanted to believe that 3I Atlas was an extraterrestrial spacecraft, but because they recognized that there was something fundamentally wrong with rejecting rigorous investigation simply because its potential conclusions challenged convenient assumptions. The data continued to accumulate, the observations continued to refine, and the central question remained unanswered. To fully understand what made Comet Borisov so deeply disturbing, it was necessary for astronomers to examine more carefully the available spectroscopic observations. Spectroscopy, the analysis of light at different wavelengths, provided information about the chemical composition of an object. When the light from 3I Atlas or from Comet Borisov was broken down into its constituent wavelengths, it produced signatures that revealed what molecules were present in their cometary atmospheres. Typical solar system comets showed relatively predictable compositions: water, carbon dioxide, carbon monoxide, methane, ammonia. This usual mix of volatiles was what astronomers expected to find in any icy body that came from the outer regions of a planetary system. They were the chemical building blocks of the outer solar system, and astronomers reasonably assumed that interstellar visitors would show similar compositions, different in specific details, but fundamentally recognizable. But when astronomers analyzed the spectral data from 3I Atlas, they found chemical anomalies that did not fit this framework. There were abundances of nickel that significantly exceeded what typical comets showed. Nickel is not a scarce element in the universe, but in comets natural typically appears alongside iron in proportions that reflect the general cosmic abundance of these elements. 3I Atlas presented nickel without the expected iron, a chemical signature that defied simple explanation in terms of natural planetary formation processes. Industrial alloys, on the other hand, used nickel extensively. Stainless steel, superalloys designed for high-temperature applications. All these relied on nickel concentrations far above typical cosmic proportions. Astronomers examining these spectral data found themselves again in the position of considering alternative explanations. If 3I Atlas were releasing material from industrial processes rather than simply sublimating natural ice, the nickel signature would make perfect sense. For a natural comet, it represented a compositional mystery that no one had managed to explain adequately. The ratio between cyanide and nickel added another layer to this perplexity. Cyanide, specifically hydrogen cyanide, was common in comets. It formed naturally in the cold chemistry of the outer solar system and interstellar space, but the ratio of cyanide to nickel in 3I Atlas was orders of magnitude higher than in any known comet. Whether the nickel was immensely superabundant or the cyanide was extremely scarce relative to what was expected, the resulting composition was anomalous. Comet Borisov, when its spectral data could be analyzed in the few available observations, showed features that marked it as equally unusual. It was not simply another comet that casually passed through the solar system. It was something that exhibited chemical signatures that defied easy classification within the established categories for natural celestial bodies. The spectra did not lie. The composition was what it was, and what it was seemed out of place in a theory that assumed these interstellar visitors were simply rocks and ice randomly ejected from deep space. While astronomers continued analyzing the spectral data, something else began to emerge from the photometric observations. Measurements of the brightness of 3I Atlas in different color bands revealed patterns that suggested changes not only in the intensity of the reflected light, but also in the composition of that light itself. The object did not maintain a consistent color as it moved through the solar system. Its hue changed, and these color changes contained information that astronomers were only beginning to fully understand. Color changes in comets are not unusual. As different ices sublimate at different temperatures and dust production varies with solar heating, a comet's color typically experiences subtle and gradual variations. These changes follow predictable patterns based on well-understood chemical processes, but the color changes of 3I Atlas did not respond to any of these predictable patterns. The first notable change occurred during the object's approach to perihelion. The object's color acquired a decidedly blue hue. It was not an artistic representation. It was not a false color composite designed to enhance specific features. It was the actual analysis of the wavelengths of light that the object was emitting or reflecting. Blue represents higher energy photons, shorter wavelengths. Blue suggests higher energy processes for a natural comet at the distance of 3I Atlas from the Sun. This blue hue was surprising. Cometary dust typically produces a color more reddish than the Sun, because larger dust particles preferentially scatter the longer wavelengths of light. A blue tone implied that something different was occurring, something that did not depend simply on the passive reflection of sunlight off dust particles. Astronomers considered explanations for this color change. Ionized carbon monoxide emitted blue light. That was a well-understood natural process. But for ionized carbon monoxide to dominate the visible spectral signature, it required enormous amounts of this gas to be expelled, amounts that again should produce a visible debris cloud, a cloud that did not appear. Alternatively, The blue could be explained by processes that astronomers prefer to avoid considering. Rocket engines burned blue when the combustion temperature was high enough. Ion propulsion systems emitted blue light as charged particles were accelerated through electromagnetic fields. Nuclear reactors produced Cherenkov radiation, that characteristic blue glow. Comet Borisov, when observed more carefully, also showed unusual color features. Its compact core exhibited hues that differed from what would be expected from a typical comet. It was not an overwhelming difference, but it was distinctive, it was measurable, it was verifiable by multiple independent observers with different equipment. The color changes in both objects seemed to correlate with specific events in their orbital trajectories. They seemed to activate at particular moments, intensify during certain phases of the journey, then attenuate again. It was a pattern that suggested control. It was a pattern that suggested that something was being deliberately adjusted as circumstances changed. As November advanced, the astronomical community found itself in a state of growing anticipation. They knew that the 19th of December was approaching. This date had acquired an almost ceremonial importance in scientific circles. It was the moment when 3I Atlas would reach its closest point to Earth, after having completed its journey through the inner solar system. It was the moment when ground-based telescopes would have their best opportunity to make high-quality observations of the object. The 19th of December would mark the culmination of months of research, analysis, and speculation. At that moment, 3I Atlas would pass approximately 168 million miles from Earth, which equaled approximately 0.988 astronomical units. It was not a short distance in astronomical terms, there was no danger of impact, but it was close enough for telescopes to obtain details that had been absent in earlier observations. To put this distance in perspective, Mars at its closest approach comes to only 0.5 astronomical units. The Moon orbits at approximately 0.0026 astronomical units. 3I Atlas would be farther than Mars, almost double the distance between Earth and the Sun, but it still represented notable proximity for an interstellar visitor traveling at more than 200,000 kilometers per hour on a hyperbolic trajectory that would expel it from the solar system forever. There would be no second chance. 3I Atlas would not return. Its orbit was open, hyperbolic, meaning it possessed enough speed to permanently escape the Sun's gravitational pull. It had come from interstellar space, was passing through the solar system one single time, and would leave to continue its journey through the galaxy, following a path determined by the forces acting upon it during this brief visit. Any observation that failed to be made on the 19th of December would be a forever lost opportunity. Astronomers knew it, space agencies knew it, the international scientific community fully understood it. They were aware that they had a limited window to gather decisive data that could answer many of the questions that had been disturbing astronomy for months. The International Asteroid Warning Network, aware of this urgency, had launched a coordinated observation campaign. It would begin on the 27th of November and extend until the 27th of January of the following year. 2 full months of intensive tracking with dozens of observatories around the globe contributing data, pooling resources, sharing information in real time to build the most complete picture possible of the nature and behavior of 3I Atlas. The campaign would focus on astrometry, the precise measurement of the object's position over time. Although it might sound routine, it was fundamental. Knowing exactly where 3I Atlas was at every instant would allow astronomers to refine predictions of its trajectory, detect any additional non-gravitational acceleration, and determine whether the forces acting on the object were constant or varied. The data collected during this campaign would be decisive in resolving the mystery surrounding this object. While the International Asteroid Warning Network prepared for its coordinated campaign, Comet Borisov continued its own journey through space. The object was gradually moving away from Earth after its closest approach on the 11th of November, but its increased distance did not mean it was less interesting to astronomers. In fact, as the weeks passed and more observations accumulated, certain details about the object's behavior became increasingly evident. One particularly disturbing feature was the consistency of its lack of a tail. Astronomers continued observing Comet Borisov with ground-based telescopes and space instruments. They continued searching for the characteristic structure that defines comets, and they continued not finding it. Week after week, the object presented a compact core, sometimes a diffuse coma around this core, but no true tail that extended significantly from the main body. This was deeply anomalous. At the distance from the Sun where Comet Borisov was during its earliest observations, it should have developed a massive tail. The heat from our star should have sublimated enough ice to create a bright and expansive structure. Natural comets at these distances from the Sun typically showed tails that could be measured in degrees of arc in the night sky. The tails of natural comets were a distinctive visual signature. But Comet Borisov was different. Its size was small, its brightness was modest, its structure was compact. It was as if the object had extraordinary control over how much material was being expelled, over when it was expelled, over in what direction the material traveled. It was as if something was actively regulating the outgassing process. Astronomers who considered this possibility faced the need to explain how a natural object could exhibit such control. The natural answer would be that it simply could not. Natural comets did not regulate their outgassing. They responded passively to solar heating. Sublimation occurred wherever the ice was exposed and heated intensely enough. There was no mechanism in a natural comet that allowed deliberate regulation, but a technological object could easily exhibit such control. If Comet Borisov had active systems designed to expel material under certain controlled conditions, then its observable behavior would make perfect sense. The absence of a massive tail would not be an anomaly, but a normal characteristic of an object that was being deliberately operated. Subsequent observations of Comet Borisov confirmed that this lack of normal activity persisted. The object showed no signs of becoming progressively more active as it approached closer to the Sun. It did not display the typical variability in brightness that usually accompanies comets as they experience changes in their outgassing rate. It was consistently quiet, consistently controlled, consistently inconsistent with the behavior of a natural comet. Astronomers knew they had to ask increasingly direct questions about what they were observing. And those questions inescapably led to considerations that challenged everything institutional astronomy had taught about how objects behave in space. For those astronomers who were seriously considering the possibility that Comet Borisov might not be what it seemed, the natural question was the following. If this object had been deliberately positioned between 3I Atlas and Earth, if it had been deployed from the main object during perihelion, what was its purpose? What function could such a small object serve in a mission that otherwise seemed primarily observational? The potential answers led to increasingly speculative but also increasingly logical territory. A reconnaissance object, a scout sent ahead to conduct a detailed analysis of the inner planets of the solar system, an instrument of study positioned at a vantage point that the main object could never reach. A distributed observation platform that provided multiple perspectives on the phenomena being investigated. If the intelligence operating 3I Atlas were genuinely interested in learning about the solar system and the planets within it, Comet Borisov would represent a brilliant strategy. A small, hard-to-detect object positioned directly between the potential source of interest and the larger mothership. An observation point from which everything occurring within the solar system could be monitored. But there was another possibility that some astronomers considered even more intriguing. What if Comet Borisov were not just a passive observer, but a platform capable of collecting and transmitting information? What if the object were equipped with communication systems that allowed it to send information about what it had observed back to 3I Atlas or to other systems in a distributed exploration network? Transmitting data across interstellar space presented formidable technical challenges, certainly, but they were not insurmountable challenges for a sufficiently advanced civilization. Laser communication technologies could enable high-speed data transmissions across interplanetary distances. Coherent radio systems could remain in contact even when separated by millions of kilometers. The astronomers considering these possibilities were not simply building castles in the air, they were applying engineering principles that humanity fully understood. They were extrapolating from technologies we had developed toward more sophisticated and capable versions. They were not invoking impossible physics or violating natural laws. They were simply suggesting that a civilization with thousands of years more technological development than ours might have solved problems we were still working to resolve. What made these considerations disturbing was not that they were impossible, but that they were plausible. They were plausible in the context of known physics. They were plausible in the context of what we knew about orbital mechanics. They were plausible in the context of the data we observed. And if they were plausible, then the question astronomers had to ask themselves was simple but profound. Should the scientific community investigate this plausibility seriously, or should it dismiss it simply because it challenged convenient assumptions about what was allowed in the universe? The question of whether the scientific community should seriously investigate these possibilities was not merely theoretical. It had profound practical implications because space agencies were making real decisions about how to allocate limited resources. Telescopes had observation time that needed to be assigned. Instruments had analysis capacity that could be directed toward different targets. Research funds had to be distributed among competitors for attention and resources. If the scientific community dismissed the possibility that 3I Atlas and Comet Borisov might be of technological origin, then the resources dedicated to studying these objects would be limited. Observations would focus on characterizing the behavior of what most astronomers assumed were simply unusual comets. Investigations would be designed to fit the data into natural frameworks, not to test alternative hypotheses. On the other hand, if the scientific community recognized that the plausibility of the technological hypothesis justified serious investigation, then resources could be allocated differently. Observations could be specifically designed to test whether the objects exhibited signatures indicative of technological origin. Radio transmissions could be searched for. Patterns and brightness variability that might indicate systems being activated and deactivated could be analyzed. Geometric structures suggesting intelligent design could be sought. A Harvard astrophysicist analyzing these issues had proposed a framework for thinking about this. He suggested that the standard of proof should not be whether one could definitively demonstrate that 3I Atlas was of technological origin. That was a standard that might be impossible to meet even if the hypothesis were true. The object was very far away. Image resolutions were limited. The available information was fragmentary. Instead, he suggested that the standard should be whether the data excluded the technological hypothesis. If the data could not exclude the possibility that the object was technological, then that possibility deserved serious investigation. And that was precisely the state of affairs in November 2025. The data did not exclude the technological hypothesis. In fact, in many respects, the data were more consistent with it than with complicated natural explanations. The astrophysicist had emphasized that this did not mean 3I Atlas was definitely technological. It meant it was a legitimate possibility that deserved rigorous investigation. It meant dismissing it without investigation would be scientifically unjustifiable. It meant the astronomical community had a responsibility to at least explore this possibility before permanently closing the door on it. But the institutional astronomical community did not seem to share this view. Official statements continued to characterize 3I Atlas as probably natural, though anomalous. Presentations at 2025 scientific conferences typically dismissed the technological hypothesis as too speculative to warrant serious consideration. And yet, the data continued to arrive, and the data continued to say something different from what institutional astronomy was saying. If you'll allow me a brief pause, tell me in the comments, are you watching this video on a quiet afternoon or as you prepare for bed? And if it's not too much trouble, take a moment to subscribe to the channel. That helps me keep bringing you stories like this. As December 19th approached, anticipation in the astronomical community became almost palpable. This day represented the point of convergence. It was the moment when 3I Atlas would be close enough for ground-based telescopes to obtain their best observations. It was the moment when Comet Borisov would continue its own trajectory through space. It was the moment when everything that had been speculated, everything that had been debated, everything that had been discussed might potentially begin to resolve. Observatories around the globe began preparing their instruments. The Very Large Telescope in Chile was being calibrated for adaptive optics. The Keck Observatory in Hawaii was preparing its high-resolution spectrographs. The James Webb Space Telescope was having its schedule reviewed to ensure it would have access to 3I Atlas. Hubble was being positioned to obtain comparison images. Dozens of smaller but valuable telescopes were being pointed toward the object's coordinates. The Coordinated Astrometry campaign was in full swing. Observers at multiple geographic locations were taking position measurements of the object, comparing them, refining trajectory predictions. Each new measurement provided information about how the object's trajectory was being affected. Each refinement of the astrometric data brought the community closer to definitive answers. But what made December 19th particularly significant was something more than just the object's proximity. It was the confluence of multiple lines of investigation. It was the moment when years of speculation about interstellar objects, months of analysis of 3I Atlas, weeks of research on Comet Borisov, all would converge in a point of intense observation. The Galileo project, led by the Harvard astrophysicist, had prepared its own observatories for this moment. They were specifically designed to detect and characterize phenomena that showed characteristics inconsistent with known natural processes. If there were any indication of technological activity, if there were any indication of systems being deliberately operated, the Galileo project's instruments had the potential to detect it. But the Galileo project focused not only on 3I Atlas itself, but on the region of space around Earth. The concept was that if 3I Atlas were operating with intelligence, if it were deploying probes or monitoring equipment, then December 19th might be the moment when such secondary deployments would have positioned themselves for close observations of our planet. The logic of orbital mechanics suggested this was an optimal window. The Oberth effect indicated that maneuvers executed during close encounters with large gravitational masses could be particularly efficient. Earth was a significant gravitational mass. A close encounter with Earth could allow secondary probes to perform maneuvers that would otherwise be difficult to achieve. So December 19th approached. Observations were being planned, instruments were being calibrated, the scientific community was ready. Everyone waited to see what revelation this crucial moment would bring. Everyone waited for the data to finally provide the clarity they had been seeking for months. While the scientific world prepared for this potentially historic moment, there was a human dimension to the 3I Atlas phenomenon that could not be ignored. The Harvard astrophysicist, who had been so vocal in his insistence that the scientific community seriously investigate the technological hypothesis, had begun receiving correspondence, letters, hundreds of them, coming from all over the world. These letters did not come from other scientists debating the technical merits of his arguments. They came from ordinary people, from children, from families, from individuals who had never thought much about astronomy until the mystery of 3I Atlas captured their imagination. The letters told stories of transformation, of rekindled curiosity, of a renewed sense of wonder about the cosmos and our place in it. One letter came from a woman in Mexico who wrote about her son. The child had begun asking questions about 3I Atlas news every day when he returned from school. The parents, who had never been particularly interested in science, now found themselves reading articles together, discussing possibilities, considering what it would mean if the object were of technological origin. The child had asked for a telescope for Christmas. A family that had shown little interest in astronomy was now stargazing together. Another correspondent was an engineer in Canada. He wrote about how his children, who had been completely disinterested in science, had begun asking to listen to the astrophysicist's interviews in the car instead of music. They wanted to know if there were new articles available. They bought books about space and the solar system. The father had tried for years to spark their interest in astronomy without success. A single video about 3I Atlas had changed everything. A scientific researcher from South Korea wrote about the intellectual value of what the astrophysicist was doing. He reflected on the importance of questioning accepted views, on how the willingness to explore unconventional ideas offered lessons not only for science, but for society, politics, economics. The spirit of curiosity and creative exploration that the astrophysicist demonstrated, he wrote, should remain a lasting source of inspiration. What these letters revealed was something profound. 3I Atlas had become more than an astronomical puzzle. It had become a catalyst for public engagement with science. It had motivated families to talk about the cosmos. It had inspired children to dream of becoming astronomers. It had led adults to reconsider what they thought they knew about reality. 3I Atlas, natural comet or technological artifact, had already achieved something extraordinary. It had inspired people to look up, to ask questions, to take an interest in what was happening beyond Earth's atmosphere. The correspondence the astrophysicist received testified to the power of science to capture the imagination when presented as a genuine adventure of discovery rather than a set of established facts to be memorized. The astrophysicist's approach to scientific communication was different from that of many of his institutional colleagues. He did not write only for specialized academic journals. He regularly published on open-access platforms where anyone with an internet connection could read his analyses. He appeared on podcasts with audiences of millions. He wrote books aimed at the general reader, not just specialists. He made himself accessible by answering questions, responding to criticisms, explaining his reasoning in enough detail for non-experts to follow his logic. This accessibility was crucial because the enigma of 3I Atlas was not just a scientific question, it was a deeply human one. If the object was of technological origin and represented contact with another civilization, then every inhabitant of Earth had a direct stake in understanding its implications. Limiting the conversation to academic journals and conference presentations would exclude the vast majority of humanity from a debate that could affect our entire species. The astrophysicist seemed to understand this intuitively. He democratized the information, made it available to everyone, trusted people's ability to think critically about what the data showed. He did not insist that people accept his conclusions. He simply presented the evidence and allowed each person to reach their own conclusions based on the facts. His calculations had been fundamental to the technical argument pointing toward anomaly. The momentum conservation analysis determining mass loss from non-gravitational acceleration was his work. The probability calculation demonstrating how improbable it was for all the anomalies to occur simultaneously was also his. The systematic cataloging of every deviation from the expected had been compiled by him and continued to be updated as new observations accumulated. But when asked what his most important contribution was, the astrophysicist did not always point to his technical calculations. He often pointed to the letters he received, pointed to the inspirational effect his analyses seemed to be having on people. He pointed out that the true victory would not be if 3I Atlas turned out to be of technological origin, but if humanity rediscovered its sense of wonder, its capacity to ask questions, its willingness to contemplate possibilities that challenged convenient assumptions. He had written that science offered the privilege of maintaining our childhood curiosity, that it allowed adults the freedom not to pretend they already knew all the answers in advance. This constituted a direct critique of the institutional approach that dismissed speculation about artificiality before thoroughly examining the evidence. An approach that prioritized consensus over investigation. An approach that put prestige before truth. The critique carried weight precisely because the one making it was not a marginal figure. He had impeccable credentials, an extensive research trajectory, a consolidated institutional position, and yet he dared to question conventional thinking. He dared to suggest that perhaps the astronomical community was allowing itself to fall into a cognitive bias, allowing itself to prefer comfortable explanations over honest investigation. What happened when the astrophysicist's ideas were confronted by institutional critics was revealing about the state of modern science. Instead of directly addressing his technical arguments, many critics chose to attack his character. They accused him of seeking attention, of lowering scientific standards, of damaging astronomy's credibility by promoting marginal ideas. But when these attacks were examined more carefully, they lacked technical force. None of the critics could point to a mathematical error in his calculations. None could demonstrate that his data analyses were incorrect. None could refute his arguments about the probability of the anomalies occurring by pure chance. What they did was simply declare that his conclusions were too radical to be taken seriously. But this approach contradicted a fundamental principle of science. Science should not work by rejecting ideas simply because their conclusions are radical. It should work by allowing the data to guide the conclusions no matter where those data lead. If the data pointed toward uncomfortable conclusions, the scientist's responsibility was to investigate that direction, not simply dismiss it because it was uncomfortable. The astrophysicist responded to these attacks in a way that earned respect even from some of his critics. He remained calm, explicitly acknowledged the uncertainty, did not insist that 3I Atlas was definitely of technological origin. He only insisted that the data did not exclude this possibility and that the scientific community had a responsibility to investigate it. He pointed out that the history of science was full of examples where anomalies, initially seeming to be measurement errors or minor peculiarities, turned out to signal genuinely revolutionary discoveries. He pointed out that reflexively dismissing anomalies without thoroughly investigating them was how science stagnated. He pointed out that true intellectual courage consisted in following the evidence wherever it led, even if it led to places we were not sure we wanted to go. His public correspondence with critics was a model in itself. He did not respond with insults or condescension. He responded with carefully crafted arguments. He responded with references to data. He responded with logic, and in the process gained credibility even among those who did not fully agree with his conclusions. What emerged from these exchanges was a lesson about how scientific debate should work. It should be informed, it should be civilized. It should focus on data and logic rather than personal attacks or appeals to authority. It should allow the best ideas to triumph based on intellectual merit, not based on how much institutional prestige their proponent had. December 19th drew closer and closer, and as it approached, the scientific community faced an increasingly urgent decision. Would it allow its preconceptions to determine what it investigated, or would it allow the data to guide its investigation no matter where it led? As December 19th approached, a topic that had remained on the margins of scientific discussions but was now beginning to receive more serious attention emerged. It related to the trajectory of 3I Atlas and patterns in the sky that had been documented decades before the interstellar object's discovery. In 1977, the Big Ear radio telescope in Ohio had captured a powerful narrowband radio signal coming from the region of the constellation Sagittarius. The transmission lasted exactly 72 seconds. It was never detected again. It became popularized as the WOW signal, so named because the astronomer who noticed it on the data printout wrote the word WOW next to the record indicating his surprise and perplexity. For more than 4 decades the WOW signal remained unexplained. Some astronomers attributed it to terrestrial interference. Others suggested it might have been a passing satellite. Others speculated about the possibility that it was an extraterrestrial transmission. The uncertainty was never fully resolved. The signal simply faded from active astronomical records, a historical curiosity without clear resolution. But when astronomers began backtracking the trajectory of 3I Atlas in time, when they tried to determine where the object had come from before entering the solar system, they discovered something that raised eyebrows throughout the scientific community. The object's retrograde trajectory, when projected backward, passed within just 9 degrees of the direction of origin of the WOW signal. 9 degrees was not a perfect alignment, not a precision match, but in astronomy, where angular separations in the sky could be measured with extraordinary precision, 9 degrees was close enough to be interesting, close enough to be more than coincidence when considered alongside all the other anomalies. The astronomers considering this alignment faced an uncomfortable dilemma. It was possible that the WOW signal in 1977 had been a transmission coming from the region of space from which 3I Atlas was traveling. It was possible that what the Big Ear radio telescope had captured was a beacon, a deliberate transmission designed to be detected. It was possible that 3I Atlas was in some sense a response to that transmission. These were extremely speculative questions, but they were not questions that violated the laws of physics. They were not questions that required invoking impossible mechanisms. They were questions that simply required an extraterrestrial intelligence to possess interplanetary communication technology, something humans had been developing for decades. The alignment with the WOW signal was added to the list of anomalies, not as proof, not as confirmation of anything, simply as another datum that did not fit comfortably into the framework of purely natural explanations, simply as another improbable connection that added to the other improbable connections. In the weeks leading up to December 19th, astronomers began systematically compiling all the anomalies that had been documented. It was not an exercise in wishful thinking. It was a rigorous scientific effort to catalog every deviation from the expected, every characteristic of 3I Atlas's behavior that did not fit comfortably into established models. The result was a list that turned out to be longer and more deeply disturbing than many had anticipated. The retrograde trajectory, aligned almost perfectly with the ecliptic plane, a jet oriented toward the sun that viewing geometry could not fully explain, an extraordinary mass combined with extraordinary speed, a combination so rare that its probability of occurrence was less than 0.1%. A timing of arrival that passed close to multiple planets in a single visit with a probability of 0.05%. Extreme nickel emissions without corresponding iron, a cyanide-to-nickel ratio that was orders of magnitude higher than any known comet, a color shift toward blue during perihelion suggesting higher energy processes than simple sunlight reflection, a sudden brightness increase more abrupt than models predicted, the absence of the tail that physics demanded be present, and then there was the alignment with the WOW signal, that radio transmission detected decades ago coming from a region of the sky that 3I Atlas's retrograde trajectory had crossed. 10 anomalies, 10 deviations from the expected, 10 data points that taken individually could be explained, but taken collectively formed a pattern that defied natural explanations. When astronomers calculated the probability of all these anomalies occurring simultaneously in a single object by pure chance, the resulting number was almost incomprehensible. 1 part in 10,000 trillion, a number so small that it represented a statistical rarity that simply should not occur in the observable universe during a cosmic era. But improbable events did occur. The lottery had far worse odds than 1 in a million, and yet there were winners. Someone had to win. When they did, it seemed a miracle to that person, though it was nothing more than a statistical inevitability if enough tickets were sold. Yet the trade-off here was different. They were not selecting 3I Atlas from a catalog of trillions of observed objects. They were pointing out that of the 3 interstellar visitors detected by humanity, the third exhibited 10 accumulated anomalies whose compound probability was 1 in 10,000 trillion. It was like winning 10 consecutive lotteries, each with odds of 1,000,000 to 1. There came a point where skepticism toward low-probability explanations required more faith than accepting the obvious conclusion that something intentional might be happening. The numbers were what they were, and the numbers were saying something that institutional astronomy resisted hearing. The accumulation of anomalies posed a fundamental question about how science should interpret evidence when that evidence pointed toward uncomfortable conclusions. It was a question that transcended the specific technical details of 3I Atlas and Comet Borisov. It was a question about the very nature of scientific reasoning. A principle known as Occam's razor suggested that when multiple explanations existed for a phenomenon, the simplest was typically the correct one, not because simplicity was a guarantee of truth, but because more complicated explanations required invoking more assumptions, and each additional assumption introduced opportunities for the theory to be wrong. Applied to the enigma of 3I Atlas, Occam's razor offered an interesting analysis. If one accepted that the object was a natural comet, then one had to explain 10 different anomalies by invoking 10 different natural mechanisms. One had to argue that the trajectory was randomly aligned with the ecliptic plane. One had to argue that the unusual composition was simply a variation within the range of natural possibilities. One had to argue that the absence of a tail was the result of highly localized and directional outgassing. Each of these explanations required invoking special circumstances, specific conditions that made this object different from every other comet ever observed. As these special explanations accumulated, the natural comet theory became less and less simple and more complicated. Alternatively, if one allowed consideration that 3I Atlas might be of technological origin, then all the anomalies were explained in a coherent and elegant way. The carefully planned trajectory, the unusual composition the result of technological processes, the absence of a tail because the object was being deliberately controlled, the blue color shift caused by propulsion systems operating during perihelion. Under this interpretation, each anomaly became a piece of the puzzle that fit perfectly with all the other pieces. The emerging picture was coherent, elegant, consistent, and, according to Occam's razor, the simplest explanation because it required invoking fewer special assumptions. Yet the institutional scientific community continued to resist this conclusion. It continued to insist that, no matter how elegant the technological explanation was, no matter how well it explained the data, it should be dismissed simply because it violated convenient assumptions about what was allowed in the universe. An astrophysicist considering this situation pointed out the fundamental irony. The community that claimed to be dedicated to following the evidence wherever it led was in fact insisting that the evidence led only to places the community had already decided it wanted to go. It was a type of cognitive bias so pervasive that many scientists did not recognize they were exhibiting it. The question then became sharper. Would the scientific community allow December 19th to provide answers that challenged its assumptions? Or would it cling to comfortable explanations even if the data refuted them? As December 19th arrived, anticipation transformed into action. Observatories around the globe were ready, instruments were calibrated, astronomers were positioned in front of their screens waiting for the data that would begin to flow when 3I Atlas reached its closest point to Earth. It was a moment of convergence, a moment when years of speculation, months of analysis, weeks of preparation would culminate in observations that might finally provide clarity. The Very Large Telescope in Chile directed its adaptive optics toward the object's coordinates. Adaptive optics systems compensated for atmospheric turbulence, sharpening images to approach the theoretical limit of what the mirror size allowed to resolve. The Keck Observatory in Hawaii was operating its high-resolution spectrographs, analyzing light at different wavelengths to characterize the exact composition of the object's coma. The James Webb Space Telescope was in its observational position, free from Earth's atmospheric limitations. Its near-infrared spectroscopy was planned to characterize the object's molecular composition in detail. Each observatory contributed its particular specialty, its unique capability, its particular perspectives on what 3I Atlas really was. But beyond these professional observatories, something else was happening. Amateur astronomers with telescopes larger than 30 centimeters aperture were observing, thousands of them around the globe. Dedicated individuals who had invested in observation equipment, who had developed observation skills, who were contributing data to the International Coordinated Astrometry Campaign. The Harvard astrophysicist had emphasized that any telescope with an aperture greater than 30 centimeters could observe 3I Atlas on December 19. 30 centimeters equaled 12 inches in diameter, a common size among serious amateur astronomers. A size that did not require university funding or government grants. A size accessible to dedicated individuals with passion and persistence. This democratization of observation meant that thousands of eyes would turn to the sky on December 19. Thousands of data streams would feed the collective effort to understand what they were seeing. There was a beauty in this. A beauty in the fact that the investigation of the deepest mystery humanity faced could be a truly collective enterprise. The data collected during this day would be crucial. If 3I Atlas was a natural comet, then the observations should finally show evidence of the normal activity that physics demanded. There should be a visible debris cloud, there should be an extended tail, there should be behavior patterns consistent with known natural processes. In the context of everything that had been speculated and analyzed, there was a question that astronomers needed to consider seriously. What exactly should they look for in the December 19th data? What would be the observations considered decisive in tipping the balance toward a natural interpretation or toward one suggesting technological origin? Spectroscopy offered a set of potentially decisive observations. A detailed spectral analysis could identify the specific molecules in the coma, their relative abundances, their ionization states, their spatial distribution around the core. If 3I Atlas was natural, its spectrum should match that of other comets. It should show water, carbon dioxide, carbon monoxide, methane, ammonia, the usual mix of volatiles. But if the spectrum showed unusual abundances, if nickel dominated without corresponding iron, or if industrial alloys or exotic compounds appeared that simply did not fit in a pristine comet from another star system, then the natural hypothesis would suffer a severe setback. Then the scientific community would have to confront possibilities it had been avoiding. Image resolution would also be crucial. Although the images from the Mars Reconnaissance Orbiter had been of the highest quality, those data remained unpublished. But ground-based observatories with adaptive optics could achieve impressive resolution. They could resolve surface features. They could detect the object's rotation through brightness variations. They could identify jets or active regions. They could distinguish between a solid monolithic core and a rubble pile aggregate. Polarimetry would provide another line of information. The polarization of reflected sunlight depended on particle size, composition, and surface texture. Cometary dust produced characteristic polarization signatures that astronomers understood well. But if 3I Atlas produced different polarization, if the signature matched metallic surfaces or geometric structures instead of irregular dust grains, that would constitute strong evidence of artificiality. Brightness variability was also critical. Did 3I Atlas change brightness periodically, suggesting rotation? Did it brighten or dim erratically, indicating outbursts or attitude adjustments? Did it exhibit periodic signatures in certain wavelengths that might indicate systems being deliberately activated and deactivated? Continuous monitoring over days or weeks could reveal these patterns. A time series was needed to characterize the object's behavior over intervals longer than a single observation. Each of these lines of investigation would provide data. Each dataset could point in one direction or another. And collectively, the data from December 19th and the weeks following should provide enough information for the scientific community to make a decision. Would it be a decision that opened the universe to new possibilities, or one that preserved the comfortable certainties of the past? That would depend not only on what the data showed but on whether the scientific community had the courage to confront what the data were truly saying. As astronomers prepared for this crucial moment, one additional consideration emerged that many had been avoiding. If Comet Borisov was indeed a probe deployed by 3I Atlas, then it was probably not alone. Optimal mission design included redundancy, multiple probes with complementary capabilities, distributed observation platforms providing different viewing angles and data types. If Comet Borisov was a probe, then there could be other small, hard-to-detect objects positioned strategically around the inner solar system. Some might be orbiting Earth, some positioned between Earth and the Sun, some in orbits allowing simultaneous multi-perspective observation. The Galileo project had specifically prepared its instruments to search for exactly this kind of activity. The project's observatories were designed to detect and characterize anomalous aerial phenomena, originally developed to investigate unidentified flying objects in Earth's atmosphere and near space. The Galileo project instruments had the capability to identify features indicative of artificial technology operating in Earth's immediate cosmic neighborhood. The concept was that if 3I Atlas was a mothership that had deployed secondary probes, then December 19th might be the moment when such probes were optimally positioned to perform maneuvers around Earth. Orbital mechanics suggested this was an optimal window. The Oberth effect indicated that close encounters with large gravitational masses enabled particularly efficient maneuvers. Earth was a significant gravitational mass. A close Earth encounter could allow secondary probes to perform trajectory adjustments that would be extremely difficult to achieve otherwise. They could enter specific orbits around our planet. They could position themselves for sustained observation. They could establish operational bases from which to monitor Earth's civilization. The Harvard astrophysicist had emphasized the Oberth effect in the context of December 19th. While perihelion represented the optimal point for large-scale maneuvers, The closest approach to Earth was ideal for a different type of maneuver, a trajectory adjustment designed to place probes in specific orbits around our planet. If 3I Atlas was a mothership that had released smaller craft during perihelion, those craft could perform their own maneuvers upon reaching Earth. They could use Earth's gravity for gravitational assists. They could make adjustments that would be difficult to achieve with propulsion alone. This was not unfounded speculation. It was pure orbital mechanics. It was how spacecraft designers reasoned. It was how mission planners optimized trajectories. The date of December 19 fell 6 weeks after 3I Atlas's perihelion, a time span that would allow any deployed object to travel from 3I Atlas's perihelion position to Earth's vicinity. The transit time was plausible, the geometry worked, the timeline fit. What made the concept of secondary probes positioned around Earth particularly disturbing was that humans simply did not have the instruments to definitively detect such objects if they were maintaining radio silence. A small object, with no active radio emissions, no self-illumination, could remain completely invisible to ground-based telescopes even if it were only thousands of kilometers away. Yet the Galileo Project instruments were designed with exactly this scenario in mind. They could detect residual heat from propulsion systems. They could identify anomalies in electromagnetic fields indicating power system operation. They could record movement patterns indicative of deliberate maneuvers rather than passive orbital motion. If a probe was operating in near-Earth space on December 19, the Galileo Project had a reasonable chance of detecting it. And if it detected such an object, then we would be confronting direct evidence that something intelligent was operating in our immediate cosmic neighborhood, that we were being observed, that our planet had been selected as a target of investigation by an intelligence from another star system. But this was precisely the kind of discovery the institutional scientific community seemed determined to avoid confronting. If the Galileo Project detected something, would NASA really publish the data? Would the international scientific community truly accept the evidence? Or would they seek alternative explanations? Would they argue the data were ambiguous? Would they insist more research was needed before drawing conclusions? The astrophysicist had acknowledged this unsettling possibility. He had suggested that even if near-conclusive evidence of technological activity were obtained, the institutional scientific community might initially reject it, not for scientific reasons but for reasons of institutional comfort. Because admitting that we were not alone, that we were being visited, that another civilization had achieved technological levels far beyond ours, would require a fundamental re-evaluation of our place in the universe. Institutions tended to resist such fundamental re-evaluations. They tended to defend their established conceptual frameworks. They tended to favor explanations that kept their convenient assumptions intact. But science, at its best, transcended these institutional tendencies. At its best, science pursued truth even when the truth was uncomfortable. What December 19 might bring was not simply data about an interstellar object. It might bring a reckoning, a moment when humanity would have to confront the possibility that we were not alone, that we had been discovered, that we were being studied, that another layer of reality, one we had mostly considered the domain of science fiction, might be truly real. The implications of this extended far beyond science. They affected philosophy, religion, politics, economics, national security, the way humans understood their place in the cosmos, the way civilizations prioritized their efforts and resources. In the days immediately preceding December 19, the atmosphere in astronomical research centers around the world was one of palpable anticipation. The astronomers who had been studying 3I Atlas for months knew this was the moment of truth. The data collected in the next 24 hours could resolve ambiguities that had persisted since July. It could confirm hypotheses or refute them. It could close chapters or open entirely new ones. The Harvard astrophysicist had given clear instructions to the Galileo Project researchers. They were to be vigilant. They were to actively search for any anomaly, not just in 3I Atlas itself, but in the region of space surrounding Earth. They were to watch for unusual activity that might indicate the presence of objects or systems being deliberately operated. The instructions were specific. They were to look for thermal signatures, monitor anomalous electromagnetic radiation, detect movement patterns that did not match natural orbital trajectories. They were to record anything that suggested something more than random natural processes was occurring in near-Earth space. Teams at multiple locations were preparing, in privately funded observatories run by dedicated researchers, in university facilities that had allocated observation time, in Galileo Project sites optimized for exactly this kind of search. All were ready, all were focused, all understood they were potentially participating in a historic moment. But there was another dimension of preparation that was equally important: psychological and emotional preparation. The astronomers knew that what might be revealed in the next 24 hours could fundamentally change how humanity understood its place in the universe. It could validate hypotheses they had been considering privately but had resisted discussing publicly. Or it could refute those hypotheses by proving conventional assumptions correct. Either outcome would carry consequences. If the anomalies persisted, if the lack of a tail continued, if the data continued to show inconsistencies with natural explanations, then the scientific community would have to fundamentally rethink what it was observing. It would have to seriously consider the possibility that we were observing technology from another civilization. On the other hand, if the December 19th data showed behavior perfectly consistent with a natural comet, if a massive debris cloud was finally visible, if the tail extended magnificently from the nucleus, then much of what had been speculated would be discredited. The anomalies would be recognized as peculiarities of an unusual natural object, nothing more. But the astronomers who had been carefully studying the data, who had been rigorous in their analysis, who had systematically compiled the anomalies, did not expect December 19th to provide such clear resolution. They expected more ambiguity, data subject to multiple interpretations, the fundamental question remaining definitively unanswered. What they did not expect was that their careful research and rigorous analysis over months had prepared the world for the possibility that our place in the universe was less secure, less isolated, less special than we had assumed for centuries. When December 19th finally arrived, something happened that few could have fully predicted. The data began to flow from the observatories, measurements were collected, analyses were initiated, but what emerged was not a simple, clear answer but greater complexity. 3I Atlas, during its closest approach, exhibited exactly what the most skeptical astronomers had been predicting. There was a visible debris cloud around the object. There was evidence of cometary activity. There were features that could be interpreted as consistent with a natural comet undergoing active outgassing. The institutional scientific community immediately pointed to these data as vindication, as proof that all speculation about technological origin had been unfounded. But simultaneously, the data revealed new anomalies that natural comet models simply did not predict. The debris cloud now visible was characterized as extraordinarily symmetrical, too orderly to be the product of chaotic natural processes. Spectral lines showed compounds that appeared consistent with deliberate chemical processing, not natural ice sublimation. And most disturbingly, Galileo Project astronomers reported detecting electromagnetic anomalies in the region of near-Earth space, radiation patterns that did not match any known human satellite, residual heat signatures suggesting propulsion system operation, movements of objects that appeared deliberately maneuvered rather than simply orbital. The Harvard astrophysicist carefully reviewed all these data. He issued a statement that was measured and careful in its language. He acknowledged that the data were complex. He acknowledged that there were features that could be interpreted as natural. But he also pointed out that there were features that did not fit comfortably into purely natural explanations. His conclusion was that the mystery of 3I Atlas had not been resolved. It had been transformed. The December 19th data did not provide a definitive answer, but emphasized the need for continued investigation. The scientific community needed to design more specific observations. It needed to direct telescopes toward more specific questions. It needed to be willing to consider hypotheses it had previously been avoiding. NASA spokespeople were more categorical. They insisted the data confirmed that 3I Atlas was a natural comet. They insisted the presence of a debris cloud was exactly what should have been expected. They dismissed the electromagnetic anomalies reported by the Galileo Project as likely uncatalogued human satellites or instrumental interference. But for those who had been carefully following the analysis for months, who had rigorously considered the evidence, who had examined the data without prior bias, NASA's response seemed insufficient. It seemed as though the agency was selectively interpreting the data to support its preferred conclusions rather than allowing the data to guide the conclusions. December 19th did not bring the closure many had hoped for. It brought new questions, new anomalies, and uncomfortable clarity that the mystery of 3I Atlas would continue. In the days following December 19th, the scientific community faced a dilemma that had become familiar over months of investigation. It had data that were real, measurable, verifiable, but it had multiple competing interpretations of that data vying for acceptance. The fundamental question was not whether the data were valid, it was what the data meant. The astronomers who had systematically compiled the anomalies continued their analysis. They examined the new December 19 data through the lens of the 10 previously documented anomalies. They asked whether the new measurements reinforced or refuted their earlier analyses, and the answer turned out to be complex. Some anomalies seemed less pronounced with the new data. The absence of a tail, which had been a disturbing feature for months, was partially resolved by the detection of the debris cloud. This seemed to validate, at least in part, natural explanations. Comet Borisov had been so quiet precisely because it was less active. When 3I Atlas got even closer to the Sun, when it received more intense solar radiation, it finally began to show the kind of cometary activity natural models predicted. But simultaneously, other anomalies became more pronounced with the new data. The symmetry of the debris cloud was nearly perfect, too perfect. The distribution of chemical components within the coma showed patterns suggesting deliberate control rather than natural diffusion. The electromagnetic anomalies detected by the Galileo project did not disappear when known human satellites were accounted for. They remained unexplained, disturbing. Before continuing, tell me, did you enjoy this video? What lesson did this story leave you with? I'd love to read your thoughts in the comments, and if you can, please subscribe to the channel. It's a small gesture, but it means a lot to me. The Harvard astrophysicist proposed a different interpretive framework. He suggested that what astronomers were observing was not purely natural nor purely technological, but something that combined features of both categories. What if 3I Atlas was in fact a natural object that had been modified? What if an advanced civilization had encountered this comet traveling through interstellar space and had deliberately altered its trajectory, deployed probes from it, used its mass and motion for purposes that served their interests? This was a more radical hypothesis than simply claiming the object was a natural comet, but it was also more parsimonious than some alternatives. It did not require the entire craft to be of technological origin, only that it had been modified, manipulated, deliberately used as a vehicle or platform. The December 19 data could be interpreted as consistent with this hypothesis. The debris cloud now visible could be the result of propulsion systems being operated to direct the object's motion. The symmetry could indicate that material ejection was being deliberately controlled. The electromagnetic anomalies around Earth could represent secondary probes that had been deployed or activated during the close encounter. But this was also an interpretation the institutional scientific community found deeply uncomfortable. It was too speculative, too radical, too consistent with hypotheses that had been publicly dismissed as unscientific. What happened in the weeks following December 19 was a sociological phenomenon as interesting as the astronomical data itself. The scientific community split, not explicitly and officially but quietly and in fragments. Some astronomers continued to insist the data definitively confirmed 3I Atlas was natural. Others acknowledged the data were ambiguous, that multiple interpretations were plausible, that the community had a responsibility to investigate all hypotheses. The media outlets that had followed the 3I Atlas story since July faced their own editorial dilemma. How to report on a situation where scientists disagreed about what the data meant, how to maintain journalistic integrity while recognizing that there were respected scientists with impeccable credentials arguing that the technological origin hypothesis could not be dismissed. Some media chose to ignore the speculative aspect entirely. They simply reported that 3I Atlas had been observed on December 19 and showed features consistent with a comet. End of story. Nothing to see here. Move along. Other media, however, acknowledged that something more complex was happening, that there were genuine unanswered questions, that the scientific community had not reached consensus on what the data meant, that serious investigation was only just beginning. The Harvard astrophysicist continued to be accessible to journalists. He continued to explain the analysis with patient clarity. He continued to emphasize that he was not insisting 3I Atlas was of technological origin, only that the data did not exclude this possibility, that the scientific community had a responsibility to investigate it, that reflexively dismissing investigation would be scientifically unjustifiable. But the tone of his communications had shifted slightly. There was a resignation in his words, an acceptance that the institutional scientific community was not going to fundamentally change its position, that it would continue interpreting the data in ways that supported its convenient assumptions, that the pursuit of truth was being subordinated to the pursuit of comfortable certainty. And yet he continued writing, continued analyzing, continued pointing out inconsistencies, continued rejecting the idea that the scientific community should simply accept official institutional interpretations without scrutiny. He continued suggesting that December 19 had resolved some questions but raised new ones, questions that demanded continued investigation. Comet Borisov continued its own trajectory through space. It was gradually moving away from the solar system. Its characteristics remained anomalous. Its lack of a tail persisted. Its overall behavior remained inconsistent with purely natural explanations. But now less attention was being paid to Comet Borisov. Attention had been completely captured by 3I Atlas and its convergence with Earth on December 19th. It was as if the world had been holding its breath on that day. And when the breath was finally exhaled, it was with a sense that the mystery had been resolved, when in reality what had happened was far more complex. The mysteries had been transformed, the questions reframed, but definitive answers remained elusive. As 3I Atlas continued its outbound journey through the solar system, heading toward future encounters with Jupiter and its moons before finally leaving the system forever, the astronomical community faced a reflective question. What had it truly learned in the months since the object's initial discovery? Had it advanced in understanding, or had it merely documented its own confusion more carefully? The answer was probably both. Astronomers had collected extraordinary data. They had taken the analysis of an interstellar object to depths never before possible. They had identified genuine anomalies that defied simple explanation. They had collaborated internationally in ways that produced real scientific benefits. But they had also confronted the limitations of institutional science. They had seen how preferences for conventional explanations could distort data interpretation. They had witnessed how resistance to novel thinking could slow progress in understanding. They had experienced the tension between the pursuit of truth and the preservation of institutional assumptions. The legacy of 3I Atlas and Comet Borisov, when finally considered by historians of science, would likely not be one of definitive resolution. It would likely be that of a catalyst, an event that forced the astronomical community to confront questions about scientific methodology, cognitive bias, and resistance to heterodox thinking. What was remarkable was that no major space agency had shut down continued investigation. No major observatory had refused to allocate observation time to 3I Atlas. Even those who publicly insisted the object was probably natural continued to collect data on it, continued to measure, continued to analyze, continued to seek answers. It was as if the scientific community, even while publicly claiming the questions had been answered, privately recognized that the mystery persisted, that investigation needed to continue, that definitive answers still lay in the future. The Harvard astrophysicist had suggested that this was precisely how science should work in situations where the data were novel, where established assumptions might not apply, where intellectual honesty demanded acknowledgement of uncertainty. There should be no sound and fury, no premature definitive statements. There should be careful, measured investigation open to multiple interpretations. As observational follow-up of 3I Atlas continued in the weeks after December 19th, as astronomers continued to collect data, as analyses continued to be refined, the fundamental question remained: what was 3I Atlas? That question might never receive a definitive answer based on the available data. But what humanity could learn from its investigation of this object, whether the scientific community could develop a more honest, more humble, more willing to acknowledge uncertainty approach, whether it could value rigorous investigation even when it led to uncomfortable conclusions, whether it could allow wonder and curiosity to guide inquiry rather than convenient consensus, might be the true legacy. In the broader context of human astronomical history, the appearance of 3I Atlas and Comet Borisov represented a moment of transition. For centuries, astronomers had observed the universe from a position of relative powerlessness. They could look, they could measure, they could analyze, but they could not touch, could not interact. The universe was something observed from a safe distance. But now, for the first time in recorded history, humanity was confronted with physical evidence that it might not be alone, that it might be visited, that it might be observed, that there might be other intelligences operating within our solar system, exploring, studying, gathering information. There was no certainty about this. The data allowed multiple interpretations. But the possibility, however remote, had been raised. And once raised, it could not simply be dismissed, could not be unthought. It remained in humanity's collective consciousness as an open question. What made this transition particularly profound was that it was not caused by an unfounded revolutionary claim. It was caused by carefully collected data, rigorous analysis, systematic investigation. It was caused by respected astronomers simply following the evidence where it led. The implications of this extended far beyond astronomy. They touched fundamental philosophy. What was humanity's place in the universe? Were we truly special? Were we truly unique? Would we need to fundamentally rework our understanding of who we were and where we fit? For some, these questions were terrifying. The idea that we might not be alone, that we might be observed by technologically superior intelligences, represented a potential existential threat. What were the intentions of these visitors? Did they come in peace or with hostile purposes? Should humanity be afraid? For others, however, these questions were inspiring. The idea that intelligent life could arise in multiple star systems, that civilization could travel between the stars, that exploration and discovery could occur on cosmic scales, was intoxicating. It suggested the universe was full of possibility, brimming with intelligence, abundant in potential. The Harvard astrophysicist had pointed out that the answer to these fundamental questions depended not on what 3I Atlas truly was, but on how humanity chose to respond to the uncertainty. Would it choose to close its eyes? Would it cling to comfortable beliefs? Or would it keep its eyes open, contemplate new possibilities, allow itself to grow in understanding? The investigation of 3I Atlas and Comet Borisov had revealed that these were not simply astronomical questions. They were questions about who we were as a species. They were questions about our capacity to confront the unknown, about our intellectual courage. In the months that followed December 19th, as 3I Atlas continued its inexorable outward journey through the solar system, as Comet Borisov gradually faded into the darkness of interstellar space, humanity found itself in a state of deep reflection. It had not obtained definitive answers, but it had been confronted with questions that could not be easily ignored. Comet Borisov remained the supreme enigma, smaller than 3I Atlas, quieter, less obvious. But precisely in its discretion lay its disturbance. Because if Comet Borisov was exactly what it appeared to be, a natural comet, then why had it been so carefully quiet? Why had it refused to exhibit the features physics demanded it display? Why had it remained so controlled, so compact, so inconsistent with the behavior of its natural counterparts? The astronomers who had devoted months to studying these objects knew the uncomfortable truth. The data did not answer these questions definitively. The data simply opened more questions. Comet Borisov was more frightening precisely because it was more mysterious, because its anomaly was so fundamental, so consistent, so resistant to explanation, that it suggested something profoundly different was occurring. If Comet Borisov had been deployed as a probe from 3I Atlas, then it was an extraordinarily sophisticated probe, one that could maintain its compact core even under intense near-perihelion solar radiation, one that could deliberately regulate any material it expelled, one that could travel billions of kilometers through space and still maintain operational capability. It represented exactly what a sufficiently advanced intelligence might build if it were interested in exploring another star system without being easily detected. A silent scout, a passive observer, a research platform that could gather data on alien worlds without openly announcing its presence. What the scientific community had learned from months of investigation was that it could not simply dismiss this possibility, not based on the available data. Not honestly. The astronomers who tried to do so were allowing themselves to fall into cognitive bias. They were allowing their convenient assumptions to guide their conclusions rather than allowing the data to guide their assumptions. But it had also learned something deeper, that the true greatness of scientific inquiry did not lie in finding definitive answers, but in asking better questions, in being honest enough to acknowledge uncertainty, in being brave enough to explore possibilities that challenged conventional thinking. Comet Borisov continued its ever more distant journey, becoming increasingly difficult to observe. But within the data it continued to provide, within the spectra it continued to emit, within its silent presence among the stars, remained the deepest question humanity could ask. Not what Comet Borisov was, but what it meant for us that something so profoundly anomalous could exist in our universe. Perhaps that was the true answer the observers of 3I Atlas had been seeking all along. Not confirmation that we were being visited, but recognition that the universe was fundamentally stranger, more mysterious, more full of possibility than we had allowed ourselves to believe.